Hey guys, today we're doing Chapter 10, Section 3. And I just want to warn you that this section is a little bit of a doozy, so I'm going to try to go through it really slow just to make sure that we really understand it. And I'm going to start by just reading a little bit out of the book, just to kind of give us an idea of what we're looking at here. So in the book, I'm on page 643, and it says, "What can you say in a situation of uncertainty? If you tossed a coin 100 times and only 10 heads occurred, then there is a great deal of evidence that the coin is not fair, because the probability of an event as extreme as this is so low. But how small must the probability of an event be before you reject the hypothesis that led to it? That depends on the situation. If the hypothesis is that the coin is fair, then you might choose a 0.05 or a 0.01 as a significance level below which you would reject it. If the hypothesis is that a person is innocent of a serious crime, then you might choose 0.000001 or 1 over a million as the level that would cause a belief that the person is guilty." So essentially what they're saying there is that depending on the situation, you want to talk about significance levels that are either more severe or less severe, just to justify that you're doing it correctly. You want as little error as possible if something's really serious, but if it's really not a big deal, like flipping a coin, then maybe you don't care as much about your significance level. The level chosen is called a significance level for a hypothesis. The most common significance levels are 0.05, 0.01, and 0.001. To reject a hypothesis for an experiment at the 0.05 significance level means that the event consisting of an experiment's outcome and all of the more extreme outcomes has a theoretical probability that is less than 0.05. Significance levels are often set before an experiment to avoid debate after the fact. For instance, in example 1, if the significance level 0.05 had been agreed to before testing the coin, and 39 heads appeared in 100 tosses, you would be obliged to reject the hypothesis that the coin is fair. Okay, so generally before we start doing hypothesis testing, which is what this section is all about, we like to think about how serious does this situation matter. So they made the comparison of putting someone on death row. Well, that's a pretty big deal. So they would want a very, very small significance level because they want as little error as possible. They want to say it is beyond a reasonable doubt that this person should be on death row. Whereas if you're talking about flipping a coin or, just proving that something is not skewed, okay, some of those things might be less of something we care about. All right, now I've got this sheet here that FST lesson 10.3. This I just kind of want to go through, and I want you to think about each of these things and kind of answer them yourself. So suppose your friend claims to be psychic. She's going to prove her powers to you by having you draw a card from a deck, and she'll guess what suit the card is. What is the probability that if your friend is not psychic, she will be able to guess the suit of the card that you drew? Okay, so we're asking what's the probability that she'll be able to guess the suit? Well, I know that there are 4 different suits in a deck of cards, so the probability is that she will guess 1 out of 4 times, right? So a 25% probability. If you draw a card 25 times and your friend correctly guesses the suit 9 times, would you be convinced that your friend was psychic? Why or why not? Well, right off the bat, you might say, no, if they're psychic, they should be able to guess it 25 out of 25 times, right? Well, let's just think about this. If we guessed it 9 out of 25 times, what is the likelihood of that actually happening? Well, if I'm using my formula, n choose k times p to the k times q to the n minus k, and I have an n value of 25, and I guessed it right 9 times, and the probability of guessing it correctly is 0.25, which means the probability of getting it wrong would be 0.75. Well, go ahead and calculate that out and just think about those odds there. Okay, number 3, how many times would your friend have to correctly guess the suit for you to be convinced she was psychic? Well, I'm sure a lot of you are saying psychic people should be able to get it right if they're really psychic. 25 out of 25 times, that's it. Okay? So again, these are all opinion questions. I just want you to think about it. And then the last one says, now suppose when you draw a card, your friend will tell you the actual card you drew instead of the suit. If your friend correctly guesses your card 23 out of 25 times, would you be convinced that your friend was psychic? Why or why not? Well, over the years, I've still heard the argument that there's no way that they're psychic if, they would have to get 25 out of 25 right. And I know that you guys just say that because you're skeptics, which is fine. But let's just think about the odds here for a minute. If I want to guess a specific card out of a deck, that's a 1 in 52 chance. So again, using this formula, my n value, let's see, I'm guessing it 23 out of 25 times. So n would be 25, my k value would be 23, my p value would be 1 over 52, and my q value would be 51 over 52. So just take a second to calculate out the odds of her actually getting 23 out of 25 of the actual card correct. It's basically unbelievable that that would ever happen. Okay, so it's really important to think about probabilities not only in the sense of, hey, if I roll 2 die, this is the probability that I get a 6 or something like that, but also in real situations, real life situations, okay? Sometimes we can be really skeptical of things, but if you actually calculate out the odds of some of this stuff happening, it might actually change your mind about, I don't know, psychics. I'm not saying that psychics are real, I have no idea, but if this happened, boy, I would be pretty convinced that they had something going on. Maybe they had a trick up their sleeve. Okay, so the reason that we talked about those things was because hypothesis testing is all about determining whether something is valid or if we want to reject it. So essentially with hypothesis testing, we always start out with the hypothesis and then we prove whether it's correct or incorrect using probabilities. So we talk about significance levels and we say, could I reject this at the 0.05 significance level, or do I have to accept that it's true? Okay, well that's essentially what we did here. We thought about these probabilities and we thought, well, okay, thinking about that probability, could that actually be something that's true? That's what we're doing with hypothesis testing. So looking at your notes, significance level is the first vocabulary word that we have, and it says the most common levels are 0.05, 0.01, and 0.001. To reject a hypothesis for an experiment at the 0.05 significance level means that the event consisting of the experiment's outcome and all more extreme ones has a theoretical probability of less than 0.05. So I just want to underline this here. Consisting of the experiment's outcome and all more extreme ones. So not only am I thinking about the actual outcome of the experiment, but I'm also calculating all the outcomes that are more extreme than what actually happened. Okay, a null hypothesis is a statement of no effect or no difference. Probabilities of outcomes remain the same. We will always assume the null hypothesis is true and then try to prove it false using significance levels. So essentially the null hypothesis is what you think should happen. So for example, I assume that a coin is going to be fair. I assume that a deck of cards will have, 4 suits and we'll have 13 of each card in a suit and things like that. I assume that a die will land on each side 1/6 of the time. So basically with your null hypothesis, it should always be something that you can calculate. For example, with a die, I should know that the probability of getting landing on each side is 1/6. And then I can maybe prove that for that specific die that doesn't work out because I have to reject my hypothesis at a 0.05 significance level. The alternative hypothesis is the other conclusion from the same experiment. So my null hypothesis might be something like, I think that the probability of landing on a 6 would be 1 out of 6. Okay? My alternate hypothesis would be that the probability of landing on a 6 is not 1 out of 6. So in other words, it's a complementary event or a complementary hypothesis to your null hypothesis. All right, let's say we're doing an experiment involving coin flips. We might say H sub naught, which is our null hypothesis, is the probability of a coin landing on heads is 0.5, and our alternate hypothesis, H sub 1, is the probability of a coin landing on heads is not 0.5. Okay? Well, using those as our hypotheses, let's say a coin was tossed 10 times and 8 heads occurred. At the 0.05 significance level, test whether or not the coin is fair. So this is our first problem here. We've already got our alternate and or our null and our alternate hypothesis, which is always the first step for a problem like this. And then we want to set our significance level, which they've already done for us. They told us at the 0.05 significance level we want to test this. Okay, so remember that we're testing all of the outcomes, including the most extreme ones. So what actually happened and anything more extreme. So the first thing I want to think about is what actually happened. Well, what actually happened was that I got 8 heads out of 10. So I flipped a coin 10 times and I got 8 heads. Now I need to think about what would be even more extreme than getting 8 heads. Well, the answer is getting 9 heads or 10 heads. Those would be more extreme things. If I flipped a coin and got 10 heads, that's less likely to happen than getting 8 heads. So what I can think about is the probability of getting 8, 9, or 10 heads. That's the probability that I want to calculate. But with a coin, remember that I'm thinking about outcomes. With a coin, when it's 50-50, or any situation that's 50-50, there's also another side to that, because I know that this is symmetric. This would be the same thing as getting 0 heads, or 1 head, or 2 heads, right? So I can also calculate the probability of getting 0, 1, or 2 heads, because those are either the same probability or a more extreme probability. So those are the outcomes that I need to look at for this specific situation, and then I can decide whether or not to reject it. So if I want to get exactly 0, 1, or 2 heads, well, I'm going to show you a new thing that you can do on your calculator in order to get that information a little bit easier. All right, on your calculator, you're going to hit second vars, and that'll take you to this distribution area, and it starts with normal PDF. That stands for normal probability distribution. Okay, we're going to arrow all the way down until we get to binom PDF and binom CDF. Okay, so these are actually really helpful because we're going to use these to calculate binomial probabilities. Binomial PDF stands for binomial probability distribution function, and binomial CDF stands for binomial cumulative distribution function. So cumulative means that we're adding up a bunch of stuff, whereas PDF means that we're just finding one specific value. So for example, if you wanted to just find the probability of getting 8 heads, you would just use the binomial PDF. If you want to find the probability of getting 0 through 2 heads, okay, so all those probabilities added up, you would use a binomial CDF. So this is actually really nice because now I don't have to go through and calculate all those individual probabilities. I can just use the CDF function in order to calculate this. So I'm just going to show you guys how to do them both, starting with the PDF. So your binomial PDF has some inputs that you have to do. So the first thing that you input is going to be the number of trials, which is also your n value. The second thing that you input is the probability of success. And sometimes your calculator will be weird and you have to put it in parentheses, and I don't really know why. And then the last one you put in is your k value. So in this specific situation here, I'm just going to go through and I'm going to calculate the probability of getting 8 heads, the the probability of getting 9 heads, and the probability of getting 10 heads using this formula, instead of using my n choose k, p to the k, q to the n minus k. It's doing the same thing, I just don't have to do all the work, which is pretty awesome. So I'm going to go to my binomial PDF. It asks me for my number of trials first, so I'm going to type in a 10, and then I'm going to hit the comma button. Then in parentheses, I'm going to put the probability of success, which they told me I'm assuming that it's 0.5. Okay. And then I'm going to put another comma. And then my k value, well, if I'm looking for 8 heads occurring, then I'll put in an 8. Okay, so this is what it should look like. And then you're going to hit enter, and it'll give you that probability. So this is going to be 0.0439. You can do the same thing for the probability of 9. So I'm just going to put in my last entry, change that 8 to a 9, looks something like this. Then I'm going to hit enter. I get 0.0097 or 0.0098. Okay, and then I'm going to do the same thing for the probability of 10. And that gives me 0.00098. Okay, so I found those probabilities using a binomial PDF. Now let's look at the probability of 0 through 2 heads. And I'm going to do this one using a CDF, which is a cumulative distribution. So for a CDF, it's the same thing. The only difference is that you're looking at 0 through something. So this is still going to be your n value, this is still going to be your p value, this is going to be your 0 to k. So you're going to just type in the k value, but it's going to give you cumulative starting at 0 up to a k value. So the binomial CDF is actually really bad if you're starting at a number like 8, like if you want to do 8 through 10, that wouldn't work out because they always start at 0. Okay, so using my binomial CDF, I'm going to start with my n value, which is 10. Okay, and then I have 0.5 for my p value. And then I'm going to go 0 through 2, so I'm just going to type in a 2 here. And this is what it should look like. Okay, then I'm going to hit enter, and that gives me 0.0547. Now you'll notice if I add all these up, I should get the same thing. Okay, so rounding, they're the same thing. Alright, and that's because those probabilities should be the same. So overall, the probability for these extreme outcomes here are going to be 0.0547 plus 0.0547. Which gives me 0.1094. So now that I found that probability of my outcome and all more extreme outcomes, I need to decide, is this something that I want to reject or do I accept? So remember that my significance level for this problem is 0.05 significance level. So if I compare this number to 0.05, I know that this number is larger than 0.05. So because those probabilities are larger than my significant level, I have to say that I cannot reject my null hypothesis. Therefore, I accept my null hypothesis. Okay, so if it was less, I would reject it and I would say, well, actually that's not true. I'm going to accept the alternative hypothesis stating that those are not equal to 0.5. But since it's bigger, I can't reject it, so I just have to say, you're right, it's 0.5. Okay, so this is an example of a probability distribution hypothesis testing problem. And this one's a little tricky because we had the heads thing, which is 0.5. Whenever you have a 50-50 chance, it gets a little weird and you have to do this. But if you don't have a 50-50 chance, you just look at the specific outcome and the less extreme ones in one direction rather than both directions. All right, let's do another one. So Roland and Diane are playing a board game with a 6-sided die. Diane boasts that she has a lucky way of tossing the die which will give her a 6 more often than normal. Roland does not believe her, so he asks Diane to toss the die 12 times. She does so and gets 5 6s. Okay, so the first thing we want to do is state a null and an alternative hypothesis for this situation. So remember, the null hypothesis is something that you can actually test, so there has to be some sort of number involved. So I'm going to say that I think that Diane should get a 6 1/6 of the time. In other words, the probability of success is 1/6. My alternate hypothesis would be that Diane doesn't get a 6 1/6 of the time. In other words, the probability is not equal to 1/6. Okay? So now I need to figure out, can my null hypothesis be rejected at the 0.05 significance level? So I need to look at the probability of what actually happened and everything that's less likely to happen. So what actually happened was that she tossed the die 12 times and got 5 6s. Okay, so she tossed it 12 times and got 5 6s. So I need to think about, that's what actually happened. What would be less likely to happen than getting 5 6s? Would it be less likely to get 4 6s, 3 6s, 2 6s? Or would it be less likely to get 6 6s, 7 6s, 8 6s? Well, the answer is that it would be less likely to get more 6s, okay? So I'm going to look for the probability that she gets 5 or more 6s. That's the probability I'm looking for. I want to know how she can get 5 or more 6s. Okay, now I don't want to go through and calculate each of those using my binomial PDF. So I'm going to actually calculate this using my CDF, but I'm going to calculate the complement because I want 0 through something. So this is equal to 1 minus the probability of 0 to 4 6s, right? So if I want to calculate that, I'm going to do 1 minus my binomial CDF. My number of trials was 12. The probability of success, I'm going to say, is 1/6. And the number that I'm going to is 4. So when I type that in my calculator, I have 12, 1/6, and 4. Okay, so this is what I've got in my calculator here. I'm going to hit enter. That gives me 0.96364. Okay, and when I do 1 minus that answer, that gives me 0.0364. So this is the probability of the outcome that actually occurred and all of the more extreme outcomes. So now I need to compare this to my significance level, and I notice that this is less than 0.05. So since this is less than 0.05, that means that I actually have to reject my null hypothesis and accept my alternate hypothesis. So in other words, at the 0.05 significance level, Diane actually does have a special way of tossing the die that makes her get a 6 more often than not. All right, that is everything for section 3.